In this video, we continue with chapter 4.1, and we now look at vector operations in Rn. So Rn you can write as just r to the n exponent, or you can use the double lines on the leg of the r to the n power, or when I'm really desperate, I might sometimes use r caret n if my font doesn't have an exponent option. So the n-dimensional plane, we're going to talk about it and we're going to do calculations with it, but I'm not going to be able to draw it if n is 4 or greater, and if n is 3, that's not going to look so great either because I'm not the best at drawing 3 dimensions. We can generalize from the two-dimensional plane R2 to an n space Rn of ordered n tuples. So an n tuple has n as the length. So for example, R1 equals just old R, the set of all real numbers. R2 equals what we can call the plane or two space, and that's the set of all ordered pairs of real numbers. R3 is 3 space, what we think of as 3 dimensions, and that's the set of all ordered triples of real numbers. So an n tuple has components x1, x2 through xn, and that can be viewed as a point in Rn with each xi as the coordinates. So if you go back to what we were doing in the plane, when I was trying to draw my vectors out here, I had 2 components, right? So for example, vector u, x1 was 2 and x2 was 4. You can imagine if I had an x3, we'd have a 3-dimensional vector coming out of the screen. And so n could go as many dimensions as we could write out. So the standard vector operations in Rn are the same as we saw in R2, and you can see how these definitions are just extensions of what we saw in the plane. So vector addition, it's still component-wise. You're adding u1 plus v1, u2 plus v2, all the way through the nth components, un plus vn. Scalar multiplication works in the same way. Scalar c gets multiplied by u1, u2, all the way through component un. And negative vector u in n dimensions is just negative multiplied by each component in here. And we can still say that vector negative u is the same as saying the scalar -1 as vector u. And subtraction works the same way. Vector u minus vector v is still the same as saying vector u plus negative vector v. And so you're going to have each component be u1 minus v1, u2 minus v2, through the nth component being un minus vn. And the zero vector is just the same. It's n dimensions of zeros. You've got n components of 0. So you can say 0, 0, dot, 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 0. Anytime you're working in n space, we can put these ellipses, the dot, dot, dots, between, usually I do it between the second component and the nth component, and that tells people that it could be arbitrarily long for your component. Okay, we are going to do some calculations in R3. I'm not going to try to draw them. And so when I did r caret 3 here, that's what I think of as R3, written like this. So I'm going to give it my best to calculate these without making any arithmetic errors. So u plus v, I'm going to do component-wise addition. So that'll be -3 plus 2 in the first component, 0 minus 5 in the second component, and 4 plus 3 in the third component. There's nothing special about these vectors. I just made them up with numbers I liked. So my first component for u plus v is going to be a -1. My second component is going to be a -5. And my third component is a 7. When you are doing vector addition, you do not have to write out all the component steps like I do. If you're doing the arithmetic in your head, it is just fine to jump from u plus v to your sum. No need to do all the component-wise steps. The other thing is, notice I didn't put my vector arrows on here, and I didn't try to write bold values for my vectors. So when you are writing vectors out by hand, totally fine, not to worry about. putting the arrows on top. I know sometimes physics professors are real picky that you have to put your arrows on top, so you're totally welcome to put the arrows on top of the handwritten vectors, but it's not necessary for me as long as your steps are correct. All right, the next calculation we want to do is 3 times u, so that's scalar 3 multiplied by u, so it's going to be 3 times -304. So we'll just do component-wise multiplication. So that should be a -9, a 0, and a 12. And then the last calculation I'll do here is v minus 3u. So luckily for me, I actually already did the 3u calculation. So v minus 3u will be 2, -5, 3. Those are the components of v. Minus, and then so that I don't mess up any of my signs here, I'm going to write out minus and then what I got when I calculated for u, because I know it's easy to make a sign error here when you've got double negatives. Okay, so then this is going to become 2 plus 9, so I believe I'll get 11 in my first component. Then -5 minus 0 stays -5. And 3 minus 12 should give me -9. And so this is my components, 11, -5, and -9 for the calculation v minus 3u. You can see in 2 or 3 dimensions, the vector operations are pretty straightforward to do by hand. If you wanted to do them in SIMPy, you can put them in as a matrix. It doesn't matter if you use column, column matrices with just 1 column, and in this case we have 3 rows, as long as you put both vectors in that way. The other thing you could do is put them in as a row matrix, so you could have 1 row and 3 columns. Either way, as long as you're consistent with u and v, if you put them in as rows, make sure both u and v are row matrices, and if you put them as columns, make sure they're both column matrices. So either way, you could check your work, but most cases it's just going to be faster to do it by hand. Okay, here are all of the properties of vector addition and scalar multiplication. Note that these are all the equivalent properties that we saw in 2 dimensions. So you can read through and see all of the same properties hold here. The 0 vector is still known as the additive identity in Rn, and -v is still known as the additive inverse of vector v in Rn as well. So you can do the same kind of proofs using the definitions as we showed for theorem 4.1 when you're working in R2 or the plane. So I am not going to go through those proofs because you already have an idea of how they work. Let's take a look at theorem 4.3. These are properties of vector addition and scalar multiplication in Rn. So V is going to be a vector and C is going to be a scalar. So the additive identity is unique. So what that's saying is if V plus U equals V, then U has to be the 0 vector. We only have one additive identity, and we know from theorem 4.2 that the additive identity is the 0 vector. Property 2 is that the additive inverse of V is unique.
I'll remind you in 30 minutes. I have a few tips for using reminders. Want to hear them?
Sorry for the background noise. My Alexa device came on, so I've unplugged Alexa, and Alexa will no longer join in our vector discussion. So we were saying the additive inverse of V is unique. So if V plus U equals 0, then it must be that U is negative V. There aren't two different vectors that could make a 0 there. The scalar 0 times V gives you the 0 vector. So imagine that's like 0 times V1, V2 through Vn. You're going to get 0, 0, all the way through 0 in the nth position. So you're going to get a 0 vector there. Property 4 is if you've got a scalar multiple times the 0 vector, that's still going to be 0 because in each component you're going to have that scalar times 0, which is still going to give you 0 in each component. Property 5, if the scalar times vector v equals 0, then it must be either the scalar equals 0 or the vector equals 0. So this is like a vector version of what you might have called the zero product property back in algebra. And so note that properties 3 and 5 both involve zeros here, but we've got two different zeros. We've got the scalar 0, that's the c equals 0, and we've got the vector v equals 0. And what we saw in property 3 is when you multiply the scalar 0 times the vector, you get the vector 0. And then property 6 says the negative of the negative v vector just takes us back to v. And we know that's true by our definition of vectors here, by the negative. So imagine just taking that negative vector definition and applying it twice the same vector, you get that same result. Let's take a look at the proof for 2 of these properties. And then you'll see you could use the same techniques to prove additional properties. So to prove the first property, the additive identity is unique, assume that v plus u equals v, and then using theorem 4.2, we can go through the steps. Now in this mock-up, we've written out in red over here all of the steps. When you do your own proofs, you're welcome to write the steps out. It's not necessary, but since you're just now learning about vectors and the steps for a proof about vectors in the textbook and in examples, we will often write out each step. But again, you don't have to list each steps as you are becoming a more experienced proof writer. So v plus u equals v, that's given to us. That's our assumption. Then I'm going to add negative v to both sides. So if I add negative v to both sides, I get a 0 on the right. And then over on the left, I've got v plus u grouped together, plus this negative v. But I know that I can do addition any order. So I'm going to change the addition in my v plus u to be u plus v. And then I know I can add in any order with grouping. So I'm going to rewrite this as v plus negative v grouped together. And v plus negative v I know is just 0. So u plus 0 equals 0 vector must mean that u is the 0 vector. So we've shown that the additive identity is unique. All right, to prove the second property, the additive inverse is unique, you're going to assume v plus u equals 0 here. And then we're going to use similar steps. So we start with our given v plus u equals 0. And then we're going to add negative v to both sides. I'm going to add it on the left just to save some time here because my v is on the left. And then by regrouping, we can get negative v plus u equals negative v. Well, we know the negative v plus v equals 0. So 0 plus u equals negative v. You can rearrange that to say u plus 0 equals negative v. This only holds if u equals negative v. So that tells us the additive identity is unique. So as I said earlier, you can represent vectors in SMPy as matrices. So you will often find it useful to represent a vector u with components u1 through un. In Rn, that's either a 1 by n row matrix, or what we call a row vector, the terms are interchangeable, or an n by 1 column matrix, or what we can call a column vector. Back when I was entering values in SMPy in earlier videos, you'd often hear me call these column vectors or row vectors. So the terms are interchangeable. This approach is valid because the matrix operations of addition and scalar multiplication give the same results as the corresponding vector operations. That is, the matrix sums u plus v if you've got row matrices here or row vectors, are going to component-wise add each entry in the matrix just as if we were doing vector addition. And the same thing if you've got columns U1 through UN and V1 through Vn, matrix addition does component-wise addition for us. So these are the same results as the vector operations of addition. I would do it on SIMPy if I had a bunch of dimensions, like if I'm working with a really big data file, I often will do component-wise addition through matrix. If it's a short matrix or a short vector that you can handwrite, you're probably in most cases gonna do this by hand. But if I gave you a huge data set, like with 12,000 entries, of course you're going to use matrices to do those calculations. So we see either way, whether we represent U plus V as row matrices or column matrices, we get the component-wise addition, the same result as vector operation. The same argument applies to scalar multiplication. So the only difference in each set of notations is how the components are displayed, whether they're as columns or rows. Our next section, 4.2, we are going to look at vector spaces. So our next set of videos will start there.